So the calculation will be performed on tin telluride, lead telluride, sorry, and we will use a 2 by 2 by 2 supercell, which is not, say, the supercell that you should use to do converged calculations. So not, but in order to go faster, now we will use a 2 by 2 by 2 supercell, and we will use a toy model, a force field that works pretty well for this kind of system. So with this kind of symmetry. Okay, so first of all, we will use so the toy model is the same that we used yesterday. So it's based on, it has an harmonic, let's say, quadratic part of the potential, and it's defined using dynamical matrices. So the dynamical matrices of this toy model are here in this directory. These toy matrices 2 by 2 by 2. So here you find the matrices that define the harmonic part of this force field potential. And for the anharmonic part, we just fix a couple of parameters in order to set, say, the anharmonic part of the potential. This P3, P4, and P4x, this defines parts of the, in terms of the anharmonic potential that define the toy model that we're going to use, okay? So we will perform the calculation using this toy model. So first of all, we have to minimize the free energy functional in order to find the SHA description of this toy model, of this system, let's say, okay? So let's perform, first of all, the minimization, okay? So let's do it, let's say, in a clean way. So let's create a directory min, and let's perform the minimization inside this directory min, okay? Then let's create a file, an input file min.py, okay? Py. Okay, I have already done it here. Just copy and paste the input file that you have here into the PDF tutorial, this part here, okay? Just copy it and paste, and just pay attention to two things. There are a couple of lines where here it's going, it's changing line, so be careful, for example, here. And also another thing that you have to pay attention here, so this DIN SSCHA name, this is in this FFD name. So what is this? I explained to you what are these two directories, these two names. This is the path to the dynamical matrices, harmonic dynamical matrices that we are going to use to define the toy model, okay? You see here I'm defining the toy model, so I'm giving the harmonic part with the dynamical matrices, and I'm defining the value of the parameters for the anharmonic part of the force field. This path, you have to change it, okay? So just remove this for spectral calculation part, okay? Because otherwise you don't point to the correct, so just remove this here. And what is this other part here? This part here is defining, let's say, the minimization. Okay, it's setting up the minimization. So first of all, I'm saying what are the dynamical matrices that I'm going to use as a starting point for the minimization. I'm using the same dynamical matrices that I use to define the toy model. Okay, I just need a starting point, so I just use the same matrices. So again, remove this for spectral calculation directory from the path, okay? Otherwise you point to the wrong direction. Okay, so probably you remember, you already done the same kind of minimization yesterday, so very fast. So here I am defining essentially the force field calculator. Here I just load the dynamical matrices that I want to use as a starting point. Then I impose symmetries in case they are not well, say, symmetrized. Then here I generate the supercell, the real space supercell according to the commensurate supercell with respect to the grid that I use to define the dynamical matrix. Okay, so in this case, for example, I have three dynamical matrices. See, din SHA3. So because this is these are the three irreducible points of a 2 by 2 by 2 grid. And so in this case, I'm generating a supercell 2 by 2 by 2. It's commensurate. Okay. Then here I create the ensemble, the object ensemble, and then I generate a number of configuration. Here I put 50. Then I'm generating 50 configuration for each iteration. I will do in general here 10 iterations because it's enough. And then here it's just minimizing, okay? I'm fixing the convolute ratio and minimum factor. So it's nothing very new for you, I guess. So here you start the minimization. And at the end, you will save in this directory, data population, the information of the last population used to generate the last ensemble that you use to do the last part of the minimization. Why I'm doing this? Because we will use this information later. And at the end of the minimization, I also print out the SHA matrices at the end of the minimization. So just copy and paste this input file and launch it with this Python main.py. I will do it again with you. So let me know if there is some problem. So this is the output. It's very fast, right? So maybe you have already done it. I don't know. And so at the end of the minimization, you have these three SHA matrices. So these are the SHA matrices at the end of the minimization for 300 Kelvin. We are doing this simulation at 300 Kelvin. And data pop here. You have essentially all the information about forces, the dynamical matrices, din gen pop1 that I use to generate the last population. So this is essentially all the information about the last step of the minimization. Okay. Okay. So now we want to compute. So it's everything clear up to now. So maybe something I don't know.
Ask.
Okay, so in the meanwhile, so now we have done the minimization. So let's, yes.
It's just a matter of just took basically the output and inputs that were in the folder already. And there's one patch that's not started. I don't know yet what. I mean, I'll follow it up, but it's just that.
Okay, you have a problem with the path. I have understood well.
Yes, it's not the same that what you were mentioning.
Right? Okay. Okay, so we have done the minimization. So now we need to create essentially the third order force constant. So the averages of the third derivative of the potential, the object that they defined yesterday, that defines this three order vertex. Okay, because in this tutorial we will just consider the bubble approximation. So the one, so we for the we just use this diagram, okay? So now we need to compute this, which is this third derivative of the potential, okay? So in order to do this, let's do, yeah, let's use the next input file here. So let's create a directory called Ashan, because this is the same script that you use to do the Ashan calculation, okay? Because when you do the Ashan, so you remember the second derivative of the free energy, we use this object as well, okay? So at the end we want to use this to compute the spectral function. So let's use the input file to compute the Ashan, and just specify in this input file that we want to print out also the Ashan. So let's do step by step. So first of all, let's go to this Ashan directory, and let's create an Ashan.py. And let's copy and paste the stuff that you have into the tutorial. Okay. Okay, let me first check if everything works smoothly, and then I will tell you line by line what is this. No. Ah, because I called this minim instead of a min. Okay, let's just change the name here from minim to min, okay? Or rename a min to minim. Okay. Okay, so let's just pay attention to the name of the directories. So we called the directory min. Let's rename it minim, okay, or just change here this part into min. And also into this minim directory, create a directory called SHA and put the SHA output dynamical matrices into this directory, okay? As you wish, I mean. Or cancel that SHA, I mean. Okay, because I don't remember if in the next I will call it again, so that's why. Okay, so once you have this script, just run it, and what let's look together what this input file does. So, okay, I'm just saying that in this script to compute this third order vertex, I'm saying that in general I have 3 irreducible points, so that I'm considering a 2 by 2 supercell, 2 by 2 by 2 supercell with three irreducible points into the 2 by 2 by 2 grid of the brilliant zone. That I'm working with matrices that have been generated, let's say at 300 Kelvin, that I'm working at 300 Kelvin, so same temperature. So here I am loading the information about the last population. Here I'm loading the SSCHA dynamical matrices. So the dynamical matrices that I obtain at the end. Everything's clear? Then here I'm just loading the last ensemble, which is into this directory, the last population generated for the minimization, because I want to use, because why I'm doing this? Because I have to compute this average, okay? So I need the last ensemble to make this average, okay? And so with this command here, I'm just generating the Hessian, and also this D3, which is this object, okay? So with this string here, I am computing this, and also this is computed, because in order to compute this, you need also this. And I'm just telling to print also D3. See, return D3 now is equal to true. Okay? And I am saving the Hessian matrices, this object here divided by the square root of the masses, and I'm also computing the tensor 3 here, okay? And so, to be precise, with this line, I'm creating this Python object, okay? This is an abstract object. Then I'm saying, okay, set up this object by using the information into this D3, which is the tensor that has been given by this routine. Then I obtain so this tensor now. Now, in general, this tensor has to be, first of all, centered. Then I have to apply the acoustic sum rule, and finally I write it on the file. So I don't know. I can tell you what is this centering very fast, or I don't know. We are already late.
No, we have time, but.
Okay, very fast. So, for example, the centering is something that you also do for a second order force constant. When you do a calculation, you use periodic boundary condition, okay? So you have a force constant like this, for example. And so something that you are in a supercell, for example, and then you have something like this, then it goes 0, then again. And so let's say this, you have done the calculation in a supercell big enough that when you are far enough, let's say the force constant, this is R, is going to 0, okay? But since you are using periodic boundary condition, your calculation at the end gives something like this, okay? It doesn't give the object that you have, which is it has periodic images, okay? In the cell that you have used to make the calculation gives this. It does not give this, okay? Now, if you use the quantity just after the calculation without centering him, okay, and you say, okay, this is my final force constant in the infinite limit, okay, but this is what we are going to do in order to make the interpolation. Essentially, you are saying, okay, so my final dynamical matrix is something like this. Then it's 0, which is, it doesn't make any sense. Our final dynamical matrix is something like this instead. Okay, so it's here, not 0, and then it's 0 here. So essentially the centering is just saying, I don't take this, I take this as my final dynamical matrix. I don't know, maybe it's not very clear, but more or less you got the message. So this is the centering. Centering is something that you have to do when you do a periodic boundary condition calculation in order to get an object that then you can say, okay, I interpolate this considering it as the result of an infinite crystal, okay? So first of all, we have to center it, and then we have to apply acoustic sum rule because the centering spoils it, okay? At least in in this version of the what is here. Okay. Below imperative. No. Okay, no.
Forward.
Ah, forward. Forward. Okay. Uh-huh. Okay, so we center it, we apply the acoustic sum rule, and finally we write it on file. And this is the file where you find this object, okay? So let's just have a look at this object. So you see in the output here I'm just imposing the acoustic sum rule after the centering, okay? And here I have my FC3. So this is the object of the third order force constant. What is the format of this object? So it's something like this. R1, R2, and then you have Cartesian atomic index. And so essentially, you can have a look, better look at how this file is organized. And into the tutorial here, I have written a small section where I explain to you how this quantity is organized into this file. But essentially, so this is the third order force constant, okay? It's just a generalization of the stuff that you see when you do a quantum espresso calculation. For example, you write second order force constant in real space. Okay. So now we have F3, so we can use this object to do the spectral calculation. Okay. So as I told you, we are in the bubble approximation. So the self energy is that I'm going to compute is this pi b. Okay. So as you see here, I have this D3, which is the third order vertex, the third order vector, and this object F here is just the, I have this, I always go to Mauri. Okay. And, okay. Okay. So here there is a 0 because as a first thing I will do a static calculation just to show you what I was saying yesterday about this static spectral function. Okay. So let's do this. The first spectral calculation that I will do is a static. It's a calculation with the static self-energy. Okay. So let's create a director here, spectral static. Okay, and let's do the calculation there. So I create this spectralstatic.py. So this calculation can be done, all this spectral calculation can be done with MPI using a parallel calculation. Since this is it's a very fast calculation, it takes, it saves more time to do it in one processor than for processors. So maybe we can just do one processor. Because when you are in API, you have to copy the information to the different in different instances. So if the calculation is fast, it's more convenient to not use it. Okay, but this is something that you already know. Okay. So first I copy and paste this thing, and then I will tell you what is the information. What is the meaning of these things here? As usual, pay attention to this change of line. Okay. be a bit more clean. Well, okay, let's see if it works. Minim action, blah, blah, blah. Okay. So first I check if it runs smoothly, and then I tell you what is the no. Ah, because no, because in this case I didn't use this SSCHA. Okay. You see, I'm just having problems with the name of the directory, so just change it accordingly. And okay, so it was very fast. So what I did with this script, essentially. So this is another thing. So, okay, so first line I import cell constructor, which is the part, it's where all this machinery about the third order, fourth order, fourth constant are done. I import this first tensor, which is the specific, say, object that we use. Then here I load the final dynamical matrices at the end of the SHA minimization, because I need two things to perform in general a spectral calculation, as you can see here from this formula. I need, see, omega, these are the eigenvalues of the SHA dynamical matrices, so I need them, okay? And also, as you can see here, everything is written in the mode basis set, where the mode basis set is the mode basis set of this SHA dynamical. So I need the information of these SHA dynamical matrices. And also I need, of course, the third order force constant. So I need to load this information here and also here. Here I'm loading the third order force constant. Here, first of all, I initialize this object. So I'm just, because the third order force constant needs information how the geometry of the system is, okay? Because he has to know how many lattice vectors, how many atoms, blah, blah, blah. So he takes this information from the dynamical matrices, for example, the SHA dynamical matrices. And once it is initialized, then you load the information from this FC3 that we have computed, okay? Then I have all the quantities, so I have to compute the self-energy. So I give an integration grid. What is this integration grid? Is this sum over k that you see here. In principle, you have to use a grid fine enough to reach converged result, okay? So now I'm just using a 2 by 2 by 2 to be fast. But in principle, you have to check if by increasing this grid, you are reaching a converged result, okay? And why I needed it, indeed, why I needed to center the first constant, because I wanted to do interpolation. Why interpolation? Because I want to be able to use k points that do not belong to the original grid, commensurate with the supercell used to calculation. Okay, so I use a 2 by 2 by 2, so I can use a 2 by 2 by 2 grid without interpolating. But if I want to use a 3 by 3 by 3 grid, then I need to interpolate. That's why I did all that machinery. So, okay. And this is just, here I give what is the point where I want to compute the spectral function. You remember the spectral function depends also on the Q point. Something like this. Q point and energy. So I'm giving in which Q point I want to compute the spectral function. And I'm computing the spectral at this point, which is x, in the point x in the brilliant zone of the system that we are considering. And now in the code it's written in 2 pi over angstrom. This is the unit that we use. Maybe in the future we will change it also to 2 pi over alat. Maybe it's more natural. And then
be careful with that units here in the spectral part. Are not the standard of quantum expressions that I use.
They match with the atomic simulation environment. So if you generate the path with the atomic simulation environment, like we did to do the dispersion, they can use those units. So if you generate the full path, giving the asymmetry point with the same way we did in the the file that plots the dispersion, these are the units. That's why they are.
Yeah, we are not crazy. But there was a reason why we. But then maybe to compare with quantum espresso, I don't know. So okay. Okay, so then so we give it the x point, and then we compute the spectral function. This is where we compute the spectral function. Okay, so spectral function get full dynamic correction along path. So what I'm doing here, I'm saying that I want to compute in general the spectral function along a path. So a path is a path of Q. So for each Q, I want to compute the spectral function. In this case, the path is just one point. Okay, but if you give a path, not a point, you will do it for all the points of the path. Then here you say what is the tensor, the third order tensor for SCHA that you are using. Here you give the grid. Here you give what is the, let's say, the energy mesh window that you want to use to make this calculation. But because the spectral function is something like this. For each Q point, you have something like this. So this is the energy, let's say. And this is the spectral function, we have something like this. Then I'm saying what is the energy that I'm considering. So from A0 to A1. And what is the step of energy that I'm considering. So this is the information given by these three values. E1 is dE E0.
Units?
Sorry?
Which are the units here?
The units are, yes, the units are in centimeter to the -1. And the temperature is in Kelvin. And then Q points, okay, this is where I give the point. So in general, it can be a path, but I'm just giving 1 point here. Then I'm specifying a static limit equal to true. If you don't give anything, it's false by default. True means that I'm blocking the self-energy with omega equal to 0. And then this is the file, the name of the file where I'm saving the spectral function, okay? So at the end of the run, you should have something like this. Okay, okay. So this is the output. So first, so these are several blocks. Each block corresponds to a Q point of this path. As I told you, we have done just 1 point, so it's just 1 block. The first column is the length along this path. It starts with 0, and in this case we have just this path, so it's just 0. So it's a meaningless column in this case. Second column is the energy, in centimeter to the -1, and the last column is the spectral function. Okay. The convention used to write the spectral function is such that when you integrate the spectral function, gives the total number of modes. So, for example, if you have a spectral function here, and then I integrate from here to here, I should have 3n, total number of modes. To be precise, yes, 3n over 2, because this is a symmetric function, so generally it's 3n over the real total axis. If you just go from 0 to infinite, it's 3n over 2, so half the total number of modes, okay? And so it's a pure number. That's why, as you can see, the unit of the spectral function is 1 over centimeter to the -1. Because when you make the integral, it must be say 3n over 2, and it must be a pure number. I showed you a figure, for example, here. See, so this is, do we have x and grace here?
I'm not sure. For me.
Let's see, otherwise. Okay, yes. So I'm plotting second column, third column. So this is the the spectral function, okay? So you have peaks, yes?
When you run the code, there is some output about time to prepare effective charges. Is this some option to include some effective charges?
Yes, yes. We take care of the fact that in this system we have effective charges.
Here we have the effective charges, right?
Yes.
They are included.
Yeah, included, yes. That's why I was saying, because in the output it's written.
Okay.
What expression? No, I just want to make the integral what is. Yes.
In the study case, the spectral function should just be a sum of the deltas.
Yes.
So, where are we giving meaning?
Okay, so in principle, you can. There is. I you say the name of a variable to give the smearing, but it's fixed by default as smearing, which is tuned depending on the because since this is just a numerical. Since these are Dirac delta, okay, so the width that doesn't have any physical meaning. We need a width just to plot it, just so right. So we fix the width depending on the automatically depending on the mesh that we have chosen. Okay, so if these two lines are closer, then the width the smearing changes accordingly in order to accommodate to have a narrow. Laurentian essentially, because the delta is nothing but the Laurentian when you do numerically. Okay. So as you can see here, but by the way, this is written explicitly in the paper. If I yeah, tell me. So what I want to say is so okay. I have also integrated here, for example, if you use X and Grace. You see, there is an integration here, and it ends up at more or less is 3, okay? And so indeed, since we have 2 atoms, the total number of degrees is 6, and so it's 3 when you go from 0 to infinite, other 3 if you go from 0 to minus infinite, because it's totally symmetric in general, in principle, the spectral function. Okay, so and also you see here you have so if you look at the SSCHA files here, in general, okay, you can have a look at it. Otherwise, here make these peaks are coincide with the frequencies of the spectral function. Okay, we coincide with the frequencies of the SSCHA. Okay. So when we do a spectral calculation in the static approximation, we are doing nothing more than just an SSCHA, okay? And so if you look at where are these peaks are really at the frequencies of the SSCHA, okay? And this is what I showed here in this figure. These vertical lines, I just took the frequencies of the SSCHA dynamical matrices, and I plot a vertical line, and you see they just coincide where these peaks are, okay? Okay, so yes.
Those frequencies can be negative.
Okay, no. The spectra, no, the spectral function cannot be negative.
No, I mean, if you plot the bands of the phonons calculated in this way, can you get negative frequencies?
You mean with the SSCHA or the spectral function? With the SSCHA, yes. That's where how you can see there is stability. So with the SSCHA, yes, because if you remember, you have structural stability when you have a curvature that like this. So you must have a negative frequency because the SSCHA is the the curvature here. So the action is done to obtain negative frequency. But if you do the spectral function is not something that describe negative frequencies, because at the end, the negative frequencies are not something physical. A system doesn't have negative frequencies. It's not. It doesn't exist in that.
But question: if you integrate then the energy from some value negative, it will appear the peak at the negative place, right?
No, you mean the spectral frequency? No, this is totally symmetric. The same that you have on the right, it's on the left. So when you have instability, essentially this stuff going to here and then disappear.
Yeah.
And here you have less weight.
Yeah, integration.
Yeah, it gives less than 3n. Okay. Okay, so let's do now. Yes.
Does the integral over the spectral function remain the same even if we have the satellite like yesterday?
Because I didn't hear. But you can reply on if you understood.
So the question is whether if you have like a more complex satellite in the spectral function, not just a delta peak or not beyond the quasi-particle picture as you were describing, the integral still is good, so it's the same.
Yes,
right?
yes.
So
It's also written here.
Yeah. So the integral will be half of the total number of modes that you have.
So it's a general sum rule fulfilled by the spectral function. It can be complex as you want. It's always.
There's another question here, right?
Thank you. Going back to the that figure that you just showed of the peak time. Yeah. So I get the peak, so that's the spectral function. But then the thing you put on top of that, and it sort of doesn't matter.
This is just the integral. I'm integrating the spectral function, cumulative integral.
Sorry.
Okay. As you can see, there is a difference here. It's twice high than this other one. It's because it's degenerate. Okay. So it's higher because it's twice degenerate. In total, you must have three, of course, 3 peaks. 6 peaks, sorry. So, and this twice degenerate one, twice degenerate one. Okay. So now let's do the same calculation, but now not in the static approximation. Let's do it in the full calculation. It's totally equivalent. It's, the input file is totally identical. The only thing that I changed here is I also specified the smearing. Why? Because now I need a smearing when I compute the spectral function not in the static approximation. Because now, if you remember, for the spectral function not in the static approximation, I have something like omega plus I0 plus. So this I0 plus means something infinitesimal positive. Okay. Of course, when you do a numerical calculation, you must give a number, and this is essentially the smearing. Okay, that we give. So you must give a smearing to make this simulation, and in principle, you have also to find the correct smearing to have converged result. So the idea is, principle, to obtain converged result, you must increase the K grid and reduce the smearing until you find the converged result, of course, with the minimum number of K points and the maximum possible smearing. But of course, the smaller is the smearing, the higher must be the number of K points that you use when integrate. Otherwise, we have jumps. Okay. Maybe you are familiar with the smearing in Quantum Express when you do smearing to compute things for metals. It's essentially the same kind of problem. When the smearing is too small, you need more K points to sample the brilliant zone. So you must find a good compromise in order to find a converged result. Okay, so in this case, just I did calculation here with 3 smearings. Okay, going from 1 centimeter to the minus 1 to 10 centimeter to the minus 1. So this is the meaning of this. Okay, let's do together this calculation. Okay. So again, I'm just loading the information that I need. So SHA and whatever. Now I'm using, as you can see, a grid more dense, 20 by 20 by 20. Actually, there is a reason why before I did a 2 by 2 by 2, and now maybe I will be more. Sorry?
I'll come after E0 in the script.
Ah, okay, then I will. There is a missing comma, yes. Okay.
And you don't need to change the static limit to false to get the whole dynamic.
Yes, maybe here. Okay, this is. I wanted to do another test here. Okay, sorry. Maybe. So what I'm doing here, okay. This is static. Maybe this is.
So it's just to test the convergence, right?
No, because there is. Okay, because there is this thing. Okay, so now we can do the calculation. Just explain so what is the. If you do a static calculation using a commensurate grid, so K grid 2, 2, 2, you must obtain exactly the same result of the action. But if you use, even in the static approximation, more K point, you are interpolating. So even in the static calculation, you are obtaining frequencies that are not exactly the same of the one that you find in the Hessian dynamic matrix. Is it clear what I'm saying? So in principle, a true static result must still, but also be converged with respect to the K grid, okay? If you use just the same K grid as the grid used to do the Hessian, so which is commensurate with, then you obtain exactly the same frequencies. But if you want to obtain converged static result, then in principle you have to increase also the K grid when you do a static calculation. Is it clear what I'm saying more or less? Okay. Okay, let's forget about this now. So let's just do a normal calculation. So static limit false. Okay, let's do a full. Let's see if it's doable 20-20-20. Otherwise, we reduce it. I'm trying to use 4 processor. Let's see. So let's look at the output in the meanwhile. So I'm saying that I'm using full dynamic correction. So what does it mean? That I'm inverting the full green function, okay? And so I'm using an integration 20 by 20 grid, and I'm using 3 smearing values, okay? So let's check how long it takes. Otherwise, we will reduce the number of. So by the way, we have done here calculation in X. Okay, so the problem of the effective matrix, effective charges actually is not relevant. The effective charge is just relevant in gamma. So if you do the calculation in gamma, okay, then the calculation will take into account the effective charges. Okay, this is something that is not taken into account when you do the Hessian. So the Hessian, just the second derivative, doesn't care about the effective charges. Okay, so when you do the spectral function in the static approximation and commensurate grid, if you are doing this in gamma, then you will see discrepancy with respect to the Hessian just when you have the split in the optimal frequencies due to the effective charges, okay? Because we take it into account when you do the spectral function, okay? But because it's because we want to something physical, okay? For the Hessian, just we want to see the instability, so that's why we didn't care about. What is the smearing? Sorry, say it again. Yes. What is the meaning of this smearing? Okay. So when you compute the dynamical self-energy, you must take essentially the limit to the real axis from above. You have something like omega plus I, 0 plus, if you remember. Yes, I made the analytic continuation and then I went to the real axis from above. That's where this mathematical things comes out, okay? In an effective calculation, of course, you don't have mathematical limits, so you need a finite positive small number to do this calculation, okay? But since so it must be small enough to reach the limit, but if it's too small with respect to the k grid that you are using when you integrate, you have numerical problems, let's say. So you must find a good compromise. So you take a k grid, then you reduce the smearing until you start seeing crazy things. Okay, then you consider a finer grid, and then you do the same until you. And then in this way you can see how it's evolving the result. And so you can study the convergence of the result, and then you can stop when you see that increasing k and reducing again smearing, you don't change the result. So you will find the good. I don't know if I'm explaining more or less.
I thought it was something like like interpolation type thing. But no.
No, it's not interpolation. No. It's just that we need something that is very small. That analytically you would do a limit. You would do a limit of a function that goes to 0. Okay. The analytical value is you take a function and this function with an argument that goes to 0. When you want to do something like this at a numerical level, you must put a positive number, smaller and smaller, in order to reach this limit. Okay, this is what smearing is doing. Okay, you are doing with the finite calculation a limit, and you're doing this with a positive small number.
Yes. Okay. Yes. So it's based on like the calculation. So it doesn't have like a physical meaning.
It's just a numerical thing. It's
Yeah.
not a physical thing.
I'll try to take it. Thank you.
Okay. Okay, so the calculation went well.
Sorry, but regarding the smearing range we have considered here in this calculation, do we have a limit for this range? I mean, we have a minimum value, a maximum value, or this range is a general range for all calculations we need to check before?
No, I mean, in general, the feeling that you have about the smearing is you more or less you develop some knowledge about what is the structure of this spectral function, let's say, and the smearing must be not too big with respect to, for example, let's say that we have 2 peaks more or less. The smearing must not be bigger than the distance, the average distance between peaks, and not too small, because otherwise you smear everything, you don't see anything, any details. But it must be, in principle, can be as small as you want, but then you need a very, very, very fine K-mesh, okay? So, in principle, you just have to check. I mean, okay, the value must be not big.
Reasonable value is a K point mesh.
Yes, not so big that it smears out all the details of the spectral function, but if it's very small, then you must use a very fine K-mesh, otherwise you have just numerical noise. So it's something that you have to check.
Okay, thank you.
Okay, so we have here 3 spectral functions. Each spectral function is for a different smearing. Okay, so the structure is the same as before, nothing new. Okay. So here I propose, let's say, another a small test. So let's try to do the same calculation, but with gamma. Okay. So let's see if you can see. So here in this plot, for example, I showed the difference between 3 curves. Okay. One is just the static spectral function converged. So it's why it's a bit different from the Hessian. Because this Hessian, this static has not been obtained with a commensurate grid, but has been obtained by increasing K 20-20-20, let's say. And as you can see, the static spectral function are just delta peaks. So nothing very sophisticated. But if you do the calculation for with the dynamic full spectral function, you see here that there is a deviation from a Lorentzian spectral function. This is the calculation in gamma. So if you are able to do it and you plot it, you should see this. So the full spectral function done in gamma is not a pure Lorentzian. You see, you have this kind of feature here. If you do it in a 4x4 supercell, not a 2x2x2 as we are doing here, you would see that the deviation from Lorentzian is even more evident. And this is the satellite that I showed you yesterday in the talk. Okay, but already in the 2x2x2 you see this feature here. So these are not converged results, of course, but already you see something weird here. Instead, here at high frequency, it's a good Lorentzian, the full dynamic spectral function. It's here that we have something weird. Okay, I will try to do the calculation in gamma so we can.
So one was regardless of how converged your static limit is, if when the static spectral function goes to 0, it's exactly the same moment that the Hessian goes to 0. No?
Yes.
So that when they are plenty close to the instability, both have that frequency has to. So
yes, but if you are because in principle, even the Hessian calculation should be converged by using bigger supercell.
Yeah.
Right.
Okay.
So.
But the zero value also should be that's the question.
I mean, for example, yeah. I don't think we see things so extreme, but in the case that you see that goes to 0 for a 20-20-20, not for the 2-2-2, yeah. Then probably the result at 2-2-2 was not converged.
Yeah. So that then what I was thinking is not correct. So
I don't know if.
Yeah, I think.
Okay. Okay, let's try to do the thing in gamma. So. So to do the spectral calculation in gamma, here just put 0. Okay, just rename this. Python. Okay, what does it mean? Oh, it's progressing here. Okay, still running. Okay, this is done. Let's have a look at it. Okay, so this is what you see. So it's a strong non-Lorentzian feature here. See, so this is not a Lorentzian essentially. So this is the spectral function for the low frequency mode here, because I choose a Windows energy that just catch this. Okay. Okay, so you can play a bit with this and try to see all the things that I was mentioning in theory yesterday. So before going on with the spectral function, let's just focus a bit on the static thing. Okay. So as I told you, when you do a spectral calculation in the static approximation, you just have peaks around the static around the eigenvalues of the Hessian. So there's nothing interesting in those peaks. The only interesting things are just the frequencies. Okay. So that's why when you want to study the static thing, the best thing to do is study something like that. Okay. What I mean, don't compute the spectral function, just compute the frequencies of the Hessian. Okay. And as I told you, when you do the Hessian calculation at first step, you just do it in a grid commensurate with the supercell. So in this case, when we did the Hessian calculation, we did the Hessian calculation on a 2-2-2 K grid. But in principle, you should converge this result by using a finer grid. Moreover, if you want to study where is instability, as also Diego showed yesterday, you should look at the Hessian, okay? But in principle, the instability, so the imaginary frequency of the Hessian dynamical matrices, could be not in one of the point commensurate with the supercell. For example, we are doing, it's not the case, this system is stable, but for example, we are doing a 2 by 2 by 2 supercell, So we are doing the SSCHA calculation. We obtain the result on a 2 by 2 by 2 grid. In principle, the system could be unstable, but the stability could be localized not in one of these 3 points belonging to the 2 to 2 grid. Could be in another point. So how to detect this point? You must interpolate, you must do the plot on the full path and find where is the instability. I don't know if I'm explaining. So for example, in this case, the SSCHA calculation gives the result only in X and gamma and another point which is not here, okay? But maybe the stability could be here. So in order to find if the SSCHA becomes negative here, you must interpolate. You must use Fourier interpolation to obtain result there. And there is a routine to do this, which is this get static correction along a path. So what we do with this routine, essentially, we compute the static correction, but interpolating the dynamical matrices for a generic path, and we use a grid to obtain a converged result integrating with a final grid. So let's try to make a calculation to see how it works. So let's copy this input file into a static.py file, for example. Okay, so just to be precise, this is not a spectral calculation, okay? Now I'm just computing the frequencies, because at static level, the spectral function is not interesting, are just peaks around the frequencies. So we don't care about the spectrum. We just care about the frequencies, okay? So this is the routine that you have to use if you want just to compute what are the frequencies in the static approximation, okay? Okay, so static.py. Okay, I copied just this. Here I'm also importing NumPy, but just because I use NumPy to make a path, okay, in a convenient way. It's not something necessary if you want. You can also load the path if you. It's not done here, but there is an option when you use this script, this routine, that you load the path from a file, okay? What I'm doing here now, I'm giving it the path with NumPy. So here I load the SHA dynamical matrices, and then I load also the third order tensor. Then here I give the integration grid. As I told you, it must be as big as possible, in principle. Then here I'm defining the path, okay? This is just a simple NumPy routine. I'm saying that I'm taking a path that goes to -x to +x, taking 100 points. This. And this is the thing that we want. So this is, so get static correction along a path. So I'm giving the SHA dynamical matrices, the third order force constant, the grid, the temperature, and the path. In principle, why I'm giving the temperature? Because in principle, you could also just check what happens if I use a different temperature with respect to the temperature that I use to do the minimization. Because this temperature affects some of if you remember the formula, there were Bose-Einstein factor somewhere, okay? So the temperature affects those Bose-Einstein factors. In principle, so this temperature here just matters for those Bose-Einstein factors. It must be consistent with the fact that the SHA dynamical matrices have been created with that temperature. So you use the same temperature. But in principle, if you change temperature here, for some reason, you just change the temperature of the Bose-Einstein factor, even if you just keep the same SHA dynamical matrices. This could be a way to check, to have a first rough view of what happens when you change temperature. Okay. Okay, so let's run this Python static Py. So again, he's loading the stuff. 300 Kelvin, the calculation. So bubble static correction. What does it mean? That I'm doing the bubble that I cancel, but at static level. And as I told you, I'm doing the static calculation, but not the spectral function, just the frequencies, because spectral function is trivial, just delta Diracs around. Okay. So at the end, we should obtain this file, V2 plus D3 static frequency dot dat. So let's have a look at this file. Okay, so these are the columns that you should have obtained. So the first column is just the length of the path in 2 pi over angstrom. Then the next 6 columns, in this case, are just the SHA frequencies along this path. Okay, in a sense, we are so because we did the SHA on a 2, 2, 2. Now we are interpolating the SHA along the path. So it's not just the 3 Q points of the 2, 2, 2. It's a generic path. And so I'm also interpolating the SHA frequencies. And then on the right, I have the SHA frequencies plus the bubble correction. So it's essentially these are the other 6 columns are the eigenvalues of the Hessian dynamical matrix vector. Okay, and then you can, for example, plot this. Let me see if, I think this is the yes. So the first 6 one are the SHA. 1, 2, 3, 4, 6. Let's say red. And the next 6 one are the Hessian. Okay. Okay, so just 2 things I want to say here. So first of all, you see here there is a splitting in gamma, and this splitting is due to the effective charge. If you look at the Hessian output matrices, you will see that you have degeneracy. So when we do the Hessian, we don't include the even when we do the SHA, we don't include the effective charges. But when we plot it, like here, then we include the non-analytic correction due to the effective charge. That's why you have a split here in the optical frequency. Okay, and then now this is not the case, but in general, what you can have that the SHA, of course, is always positive, so you will always see that the SHA doesn't have any softening, but maybe the blue line could be at a certain point become imaginary, or then it means that you have found an instability, and that Q point gives you the instability pattern. Okay, so this is the tool that you must use if you want to see instability in a system. Okay, because in principle, I repeat again, instability could be in a Q point that does not belong to the grid that you use to do the SHA calculation. Okay, so you have to interpolate. Because another way you could do, for example, you could take the Hessian dynamical matrices on the 2, 2, 2, and then use MAT-DIN of quantum espresso, and then you interpolate. But this is different from what I'm doing here. What I'm doing here, I'm applying the correction point by point. So I'm interpolating also the correction, and I'm adding. If you do instead the other way around, the MAT-DIN from quantum espresso just from the Hessian, you are taking the result and you are interpolating the full result. You are not interpolating the correction and adding so it's different. And this second thing is the correct one. So you should compute at each Q point the correction by using interpolated third order matrices. Okay, so this was just to show you the static, a typical static calculation. Okay, so now we go back to the spectral functions. So what we have done so far is a spectral calculation with the static approximation and full spectral calculation, okay? As I told you, the full spectral calculation can be expensive because you have to invert a big matrix, and also doesn't allow you to understand if you can split the contribution to the spectral function from different modes. You remember yesterday I mentioned what I call the no-mode mixing approximation. So if I can say, okay, the spectral, each mode has a different spectral function. So in order to do that, there is a specific routine that is called get diagonal here, dynamic correction along path. So I compute the spectral function, but in the diagonal no mode mixing approximation. Okay. So let's see together what is the result. So let's create, I don't know, spectral. Okay, let's copy and paste. So what I'm doing here, essentially, it's always the same story. So here I want to give a path. I'm just doing it in gamma. K grid is the integration grid that I'm using. Here I'm loading the third order force constant. Here I'm giving the energy window with the mesh 0.1 centimeter to the -1. And this is the smearing. I'm just doing the calculation for one smearing, okay? But in principle, you can do, you must check convergence with respect to the smearing. Okay, so this is the thing. Let's run it. So, in the meanwhile, I want to show you something. No. So the guy that asked me about the smearing, so this is the formula, okay? If you look, this is the smearing is here, see? It's just a positive number that enters here. This is an analytic formula that has this object at the denominator. In principle, you should do the analytic limit for this that goes to 0. Of course, we cannot do it when we do finite calculation, so we just use a positive number. That's it. But if you are in the static limit, this is just 0. So you don't need it, okay? But in principle, you have a smearing for the, okay, I didn't write it. Okay, so what we are computing now is the spectral function in the no-mode mixing approximation. So I'm computing this, okay? I'm writing the spectral function as a sum of the spectral function for the different modes. Remember, I cannot do this if I am in the full spectral function mode. I can do this only if I'm neglecting the mixing between different modes. And for each mode, this is the formula. So it's a kind of Lorentzian, but which depends on the variable here. So it's not a true Lorentzian, see? So this is what I'm computing now. This is 79. Okay. So this is the output. Okay, let's have a look. So this is the spectral function. So this is the spectral function in this no-mode mixing approximation. In principle, as I told you, you could give a path, but I didn't give any path, just one point. If you give a path, you have several blocks, one block for each Q point. Now we have just one point, so just length 0. The first column is the length along the path. Then we have the energy, so the different value of the energy, that goes from 0 to 150. This is E1 that they give. Then you have the spectral function, the total spectral function, the third column, which is this sum here, 78 sigma. And then, but I also write the component for each mode. So you see, since we have 6 mode, I have 1, 2, 3, 4, 5, 6 modes, okay? So if you want to see, for example, let's have a look. Okay, let's plot, for example, the total spectral function. Second column, third column. So this is the spectral function in gamma. Okay, I didn't, in principle, okay. This is, the first peak is just the acoustic peak in gamma, which is trivial. Of course, you must have this peak, so it's not very interesting. Okay, so these are the other peaks that come from the optical mode, and you have a splitting due to the effective charge. Okay, so this is the total spectral function. Let's see now component by component. Okay, so for example, 4. How is here now? This is the acoustic, so of course it doesn't. So 4, 5, 6 doesn't care. 7. Okay, so the 7th mode is this green line here. 8 is the same, so they sum up and give this this peak here, and the 9th mode is this one. Okay, it's yellow is a bit. Okay, so by using these features, you can take the full spectral function and you see, okay, this comes from this mode, this comes from this other mode, and so on. You can do this only if the no-mode mixing approximation is appropriate. Okay, so let's go to the next step. No, maybe here we have, okay, yes. So what I've plotted now is this 79, okay? But as I told you yesterday, this is not a Lorentzian, but maybe it could be possible to approximate this not Lorentzian with a true Lorentzian. So something like this, where you have a fixed center and a fixed width, okay? So this routine tries to do that. We already know that for the last mode, it will work because it was clear that it was a Lorentzian. And we already know that for the other 2 modes, it doesn't work, it's not Lorentzian. But it will try, in any case, to approximate with the Lorentzian. And it uses 2 kind of approaches. Okay, one is to give this as center. This is what I called yesterday one-shot approximation. So you take this, essentially it takes this 80 zeta. This real part gives the center. The imaginary part gives the weight. And instead of taking a function, omega, it just fixes omega in the SHA frequency. This is what I call a one-shot approximation. So this gives a tentative center and a tentative width for a Lorentzian approximation to the spectral function. And he also does try to use the perturbative approach that I said yesterday, that works when the spectral function is much smaller than the SHA frequency. Okay, so this is what is done here in these 2 files. Frec dynamic. Okay, so let's try to plot it. Let's see how it works. So spectral function Lorentz one shot, for example, and let's compare it with Okay, just it is the same structure, the file as the normal, the other spectral function. Just is a sum of Lorentzian now. Okay, and spectral function. Okay, so this is the result. Of course, in gamma and zero, we have just the acoustic peak, with that we don't care. Okay, so this is the result. The red, the black is the Lorentzian approximation, and the red is the correct one. As you can see, for the last mode here, it was pretty good. It's pretty good, the Lorentzian approximation. Okay, there is a difference, but it could be also a numerical problem, and doesn't matter. Whereas for this mode here, you see that the Lorentzian approximation is pretty bad. So this excitation here, the energy of this excitation, it's not properly described by a quasi-particle. Okay. Okay. And this is. Okay, so when you use the Lorentzian approximation, you at the end have a frequency and a width, right? Because this is what characterizes a Lorentzian, the center and the width, which is the frequency of that quasi-particle and the line width is related to the line width of that quasi-particle. We also write in a file this information, okay, which is here. Less frequency, V2 frequency shift, half width at half maximum. This is the meaning of this one shot, okay? So what is the meaning of this? Okay, the first column is always the length. In principle, we have done this for several Q points. Now we are just doing it for gamma. Then we have the SHA frequency for this point, the first 6 column in this case. Then we have the frequency shift. What is the frequency shift? Because when you do, if you remember the figure yesterday, when you do the Lorentzian, so the situation is this. So if this is the energy, so you have, this is the SHA frequency, and then using doing the Lorentzian approximation of spectral function, you have something like this. Okay. So this is my frequency in the Lorentzian approximation, and what I call a shift, the energy shift, is this object here. Okay. So this is this shift that you have here, and also you have this quantity here. I took half of this object, and this is what I call half width at half maximum, okay? So this is the information stored here. Then if you take the shift, you sum to the SHA frequency, you obtain the correct frequency. Now in principle, the frequencies, when you apply the shift, they could change order. For example, if you have a frequency 1, then a frequency 2 here, for example, then you apply the correction, the shift could make this going here, for example, okay? So essentially, the code apply the correction and then order them in order to give you a file with the correct order of the corrected frequencies, okay? This is convenient when you want to plot it, otherwise it's a mess, okay? So this is what you find in this other file here. This frequency dynamic, one shot and perturbative, because as I told you, we applied 2 different techniques to approximate the spectrum with the Lorentzian. The dynamic 1, 0, 0, dynamic, one shot. Okay, so you see SHA frequency plus shift sorted, because in principle the order could be different from the SHA one, and the corresponding half width at half maximum sorted as well, of course, to match. So in this way, you have the first half width half maximum is the corresponding to the first of the frequency and so forth. Okay. this gives you two files just to see, first of all, what is the correction, and then to have a final file that you can use to plot. Okay. We have almost done, I think. Okay, yeah, we could do this exercise, but maybe we are already a bit late, maybe. So, yeah, so let's move on. So this is, so you can use the same get one, okay, so at the end of this calculation, we have a file with the frequencies and the line width done with the one-shot approximation and the perturbative approximation, okay? There is a way to do this faster instead of doing this, because this get dynamic correction along a path gives you the full spectral function in the no-mode mixing approximation plus the spectral function with this Lorentzian approximation. But maybe you are just interested in line width and frequency in the Lorentzian approximation. You don't want the full spectral function. Then you can use this, this routine here. Get one shot or perturbative dynamic correction along a path. So this is used to just have frequency and line width without caring about the full spectral function in the no-mode mixing approximation. Okay, so you are essentially already doing just the Lorentzian approximation. Okay, I just describe it now. So if you do this, essentially you obtain a file that you can plot, and this is, for example, in this case, what we have. We have the frequency corrected, and this with this blue line here, I just use, you can use this GNU plot script to do that, and then here we have the line width. Okay, so I used the line width just to give an error bar, let's say. In this way, you can plot the frequency and also the uncertainty. But of course, this is appropriate if the Lorentzian approximation is good. As we have already seen, in reality, for this frequency here is not good because this is strongly non-Lorentzian. We have a satellite. And so, if you try to use a color plot, to make this figure, this is what you obtain actually. Now you have this kind of satellite here, okay? This figure has not been done with a 2x2x2 supercell because it's not very clear. If you do at home the same calculation with a 4x4x4 and just use a GNU plot script, for example, to do a color plot, this is what you see. So, but we have already seen it just in gamma. This is just to have a fancier picture, okay? Okay, I think that's more or less. Okay, so this last. When you do this get once or OS perturb dynamic correction along a path, of course you can change the grid used to the calculation and the smearing. As I told you, in principle, you should do a convergence check to do that. So you do this calculation for different grids and different smearing, and then you plot it. What I'm plotting here? I'm plotting here the half width at half maximum as a function of the smearing, of the used smearing for different K-mesh, integration K-mesh. So, for example, if you use a 4x4x4, you see that the smearing does this, okay? Then you do an 8x8x8, is totally different. So for sure, the 4x4x4 is not enough. Then you, for example, use a 16x16x16, and you see that for high smearing, they overlap, and then they change just here. This is normal. In general, when the smearing is big, the different K-mesh don't make a difference. It's when the smearing is becoming smaller and smaller, then you see a difference, okay? And of course, the correct one is the one with more K points. So in this case, you see from 8, 8, 8, 16, 16, 16, and 31, 32, 32, 32, you see there is a deviation just around here. So essentially the converged value is this one that you can obtain with more or less, I don't remember here how much, but it's 0.5 smearing to centimeter to the minus 1 using, and you can use, for example, a grid of even 8 by 8 by 8, or even better, 16 by 16 centimeters. So by doing this test, you know that in order to do calculation, these are the parameters that you have to use: 16 by 16 by 16, and smearing this value. Of course, this is just done for one Q point. In principle, you have to do this for different Q points in order to have a global overview of what are the best parameters that has to be used in order to do a proper calculation. Okay, I think I'm late, so